Hello, my name is Reza Alijani. I'm a fifth-year PhD student at Duke. I'm explaining our paper Predict and Match Profit Inequalities with Uncertain Supply. This is a joint work with Sid Banerjee, Srinivas Kulapati, Kamesh Munagala, and Kaim. I start my presentation with explaining the first profit inequality introduced almost 40 years ago. In this problem, there is a gambler and there are n boxes. One distribution is associated with each box, and there is a reward inside each of these boxes. The value of the reward is drawn independently from the corresponding distributions, and the gambler only knows the set of distribution and not exactly which distribution is associated with which box. Boxes arrive one by one sequentially, and the gambler can open each arriving box and see the value inside of it. Then he can either choose the current box and get the reward, or he can discard that box and ask for the next. The goal here is to maximize the gambler's reward. And the main question is to design the optimal policy. However, such an optimal policy can be very complicated. So we are looking for an approximately optimal policy. We can define a benchmark which is stronger than any policy, including the optimal. This benchmark is known as profit, and she actually knows all the realized value and can choose the box with the highest value. So if we show that a policy is guaranteed to be at least if we show that the expected reward of a policy is guaranteed to be at least half of this profit, we know that this will be at least half of the optimal policy as well. And for this problem, it turns out that there is a too competitive strategy, which means that there is a strategy such that a gambler who follows that strategy in expectation gets at least half of the expected value of a profit who knows everything. This type of inequality is known as profit inequality. Another interpretation of this inequality is that a profit who knows everything only has a bounded advantage over a gambler who only knows distributions. So this type of inequality captures the value of information as well. Now I have defined the basic profit inequality, and I want to introduce an important family of strategies for a gambler. This family is known as threshold strategies. In a threshold strategy, we set n different thresholds for these n boxes, and we choose the first box whose value is greater than the threshold for that box. These thresholds can be the same for all of the boxes. In that case, we call it a fixed threshold strategy, but it doesn't have to be like that. Note that the threshold does not depend on the realized values of previous boxes. So we can set all of the thresholds up front without opening any box. And actually, for this type of strategies, we don't even need to open a box. The only thing that we need to implement this type of strategy is that we should be able to ask if the value inside that box is greater than the threshold or not. For the basic profit inequality, it turns out that there is a too competitive fixed threshold strategy as well. And in order to see why these family of strategies are important, we need to look at the problem from a different perspective. Instead of a gambler and a set of n boxes, consider a seller with one single item who wants to sell it to a stream of buyers who arrive one by one. And the value of buyers are private information. The seller only knows the set of value distributions. And the goal is to maximize social welfare. This is exactly the same problem. And a threshold strategy in this perspective is actually a posted price mechanism, that we set a price for each arriving buyer. They accept the price if their value is greater than that, and they reject it otherwise. There are two main properties for these type of mechanisms. First, they are simple, and second, they are incentive compatible. Now I want to just mention one generalization of this problem as known as multiple choice profit inequality. In this generalization, we have m identical items, and both the profit and an algorithm can choose up to m buyers and allocate items to them. There are two important results regarding this problem, and the point that I want to highlight about these results is that the competitive ratio approaches 1 as m becomes large. Now, I want to introduce our variant. We add supply uncertainty to the multiple choice profit inequality. Our items are present and are identical. Items are present initially, but they are not in the system until all the buyers show up. So items might disappear after some time. There are two main motivations for this problem. The first one is that items might be perishable, and the second one is two-sided markets, and items might be controlled by different sellers, and these sellers might leave the system after some time. Now, let me define the problem formally. We have m identical items. All of them are present initially, but they might disappear after some time. We call this time the horizon of that item. We know the horizon distributions, and the actual horizon is drawn independently from the corresponding horizon distribution. If the horizon of item I is hi, that item only can be allocated to one of the first hi arriving buyers. We have IID buyers, and the value of buyers are drawn from a common distributions. And each policy needs to accept some of the buyers. And if a policy accepts a buyer, it needs to match it to an item that has not departed so far. The goal is the same as multiple choice profit inequality. We want to maximize social surplus, and the benchmark is a profit that knows everything, which means the profit knows the realized values and also realized horizons. I want to summarize our results. Our main results hold for the case that horizon distributions satisfy an MHR property. For the multiple item setting, if horizons are independent but not necessarily identical, and they satisfy MHR property, we can achieve a constant competitive. And we can also show that there is a constant lower bound for this problem, unlike the multiple choice. So the competitive ratio does not approach 1 as m becomes large here. And also we can show that if we don't have that MHR assumption, then there are instances such that the competitive ratio is unbounded. So we cannot hope for a constant competitive ratio. We also consider the more specific single item setting, and we show that for this setting, there is a fixed pricing policy which has 2 minus 1 over mu competitive ratio, where mu is the mean of the MHR horizon distribution. We also show that this result is tight for the single item setting, which means that for each mu, there exists a MHR horizon distribution between mu, such that no policy is better than 2 minus 1 over mu competitive. Now I want to explain our constant competitive algorithms. I start with the simpler single item case. For this case, as I said, the result holds only when the distribution satisfies the MHR property, which means that the probability that item departs becomes larger as time goes on. The formal definition can be seen in the slide. For this setting, first we find an upper bound for the profit, and then we show that we can come up with a policy that achieves a constant fraction of this upper bound in expectation. In order to find this upper bound, we use an LP relaxation. There are two main constraints for our LP. The first one is that the item should be sold at most once in expectation. And the second one essentially says that we can allocate the item to a buyer with value V only if such a buyer shows up before the horizon of the item. If we take the Lagrangian of this LP and follow some simple steps, we can get the upper bound shown in this slide. This upper bound actually suggests a price itself, and I call this price the price suggested by the LP. Actually, we could have achieved this upper bound. We could have achieved this upper bound exactly if we had infinitely many buyers and also infinite horizon. However, if we set this price, there is a chance that no buyer accepts our price, and in those cases we get 0 as our reward. However, we show that if we set that price, we can achieve actually a 2 minus 1 over mu competitive policy. In other words, we show that the probability that no one accepts that price is not that large. An interpretation of the algorithm explained is as follows. We can pretend that our item departs uniformly over time, just like a geometric distribution. And then our algorithm is like balancing the rate of acceptance of buyers with the rate of departure of the item. So that's just an interpretation of the algorithm. Now I want to explain the more complicated setting in which we have multiple items. Both the algorithms and the analysis is much more involved for this case. Similar to the single item setting, first we want to find an upper bound for the profits welfare, and then we want to come up with an algorithm that is a constant approximation for the upper bound of profits welfare. In order to find an upper bound for profits welfare, we divide the time into stages such that the expected number of items departing during each stage decreases exponentially. And then we find an upper bound for profits welfare during each of these stages separately. Again, we use an LP relaxation, and the main constraint here is that expected number of matches during a stage is at most expected number of items available at the beginning of that stage. Here by available, I mean has not departed before beginning of that stage. And then I'm not showing the upper bound, but it just follows some simple steps, and it looks similar to the upper bound for the single item setting. By that I mean the upper bound suggests the price again, and we use that price later in our algorithm. In order to explain our algorithm, we divide the time according to the new division in this picture. Each stage in this new division corresponds to a stage in the old division, and the goal is to design an algorithm such that the expected value that algorithm achieves during each stage in the new division is a constant fraction of the profits welfare during the corresponding old corresponding stage in the old division. So here, during prime 1, we want our algorithm to achieve welfare, which is a constant approximation of the profits welfare during S1. During S prime 3, we want our algorithm to achieve welfare, which is a constant approximation of the profits welfare during S3 and so on. In order to do this, at the beginning of each stage S prime 2 k minus 1, we choose each available item with a probability equal to its departure probability during S2k as a potential match for this stage. So it's like we skip stage S2, but actually we kind of simulate the departure event during S2 by choosing each item available at the beginning of prime 1, which is essentially all of the items, with probability equal to their departure during S2. So at the end of S prime 1, the number of available items expected, the probability that an item is available is actually equal to the probability that that the same item has not departed at the end of S2. This is because an item can become unavailable because of its departure or because of the process of choosing as a potential match for an stage. Now we use the suggested price of LP for a stage S2k minus 1 and match an accepted buyer to one of the available potential matches. If there is no potential match left, then we just don't accept any buyer anymore. And also at the end, we discard all the potential matches, even if they remain unassigned and available at the end. With this process, we guarantee that at the end of, for example, S prime 3, or at the beginning of S prime 5, actually, the probability that an item is available is not less than the probability that an item has not departed before beginning of S5. Here, available means not departed and has not been matched to an accepted buyer. So we have this, and also with this process of discarding, even if they stay unmatched, we guarantee that the events that two items are available at some points are totally independent. Now we can use some concentration inequality and show that the expected welfare of our algorithm during each stage is a constant approximation of the profits welfare during the corresponding stage in the old division. So with this algorithm, we can guarantee a constant approximation of the profits welfare during odd stages. We can do exactly the same thing for even stages, and we can run one of these algorithms with equal probability, and this will be a constant approximation for the total profits welfare. I did hide some details. Actually, we need to handle some special cases separately, but I just wanted to point out the high-level idea. And here we can see 3 future directions. Yeah, I want to finish my talk at this point. Thank you.